Hello guys, and thank you for watching this video lecture. Today we want to study discrete uniform distribution in Python. Discrete uniform distribution is a simple discrete probability distribution where a finite number of outcomes are equally likely. So in today's lecture, we will see the definitions, properties, mathematical formulation like PMF, CDF, mean, and variance. Then we will see several examples, and also we will try the examples in Python. The first question is, what is the discrete uniform distribution? We use discrete uniform distribution to model a random variable like x with a finite set of equally likely outcomes. It means the probability of all the outcomes is the same. For example, rolling a pair die. So the outcomes here are 1, 2, 3, 4, 5, and 6, and the probability of each one is 1 by 6. Right? Or, for example, drawing a card from a deck. We have 52 cards in total, and probability of each one is 1 by 52. Or selecting a random day of weeks. So we have 7 days, and probability of each one is 1 by 7. So for integers, we have some bound, minimum value and maximum value. In here, a is 1, b is 6. In here, a is 1, b is 52. In here, a is 1, b is 7, right? So when we have the lower bound of like a and the upper bound like b, then the number of outcome is b minus a plus 1. If 1 is, we want to consider the last one as well. In uniform distribution, we have only two key parameters, a as the lower bound, it's an integer, and also b as the upper bound, and also it's an integer, and b always must be greater than or equal to a. Next, PMF and CDF, the probability of any outcome like k, probability of x equal to k is 1 by upper bound minus lower bound plus 1, right? And this k is something between a and b. For example, for a fair die, a is equal to 1 and b is equal to 6. So probability of x is equal to k, it's equal to 1 by 6. Next, we go for cumulative distribution function. The cumulative distribution function, it means this one, it means the probability that x is less than or equal to x. This one equals to the integer part of x, floor of x, you can say integer part of x, minus lower bound plus 1 divided by upper bound minus lower bound plus 1, and x is something between lower bound and upper bound. So the result will be something like a stepwise function, where for x less than a, it will be 0, the CDF will be 0, and for x greater than or equal to b, it will be 1. So in this example, what is the probability of rolling less than or equal to 3? It means x is less than or equal to 3, right? A small x is equal to 3. So in this case, f of x, or you can say f of 3 is equal to 3 minus 1 plus 1 divided by 6 minus 1 plus 1. 3 minus 1 plus 1 is 3, and 6 minus 1 plus 1 is 6, which is equal to 0.5. Next, the mean, the average outcome is the midpoint. Easily, this is the midpoint. A plus b divided by 2. The variance is the measure spread of outcomes. Upper bound minus lower bound plus 1 is power of 2 minus 1 divided by 12. Okay, now let's go for Python coding to see the behavior of uniform distribution. We want to go for 1000 random sample spaces from a discrete uniform distribution for our integers 1 to 6. So for that one, first we import numpy as np, then we will import matplotlib.py plot as plt. In scipy, we will import randit. This is for discrete uniform distribution functions. So from scipy.stats, import randint. Next, we set random seed for reproducibility, np.random.seed42. So this ensures consistent random numbers across different rounds that we are going to have. So our parameters a is equal to 1, b is equal to 6, and number of samples is equal to 1000, right? Then we will generate discrete uniform random samples. So data equals to randint dot random variables, and we will pass the parameters a, b, and size is equal to n samples. This will simulate 1000 samples from uniform like a and b. In here, we should consider b plus 1 because randint upper bound is exclusive. So 1 plus 1 should be here. Then we will calculate mean and variance. So we should execute this one. So we can print the mean, print f mean is np.mean data2f 3.46. In the same way, we can go for variance. Print f variance is np.var of data, and here we will go for the same 2f. Okay, 293. This is the simulation mean and simulation variance. If I want to go for theoretical mean, so print f theoretical mean will be a plus b divided by 2. which is 3.5, a little bit different because of simulation. We can also print the theoretical variance b minus a plus 1 and all minus 1. So here is the theoretical variance for uniform distribution. We can also go for plotting. We can plot the histogram of simulated data. So plt dot figure and fig size is equal to like 8 and 6. 8 and 6. Then here plt.hist, and we will get our data, and then beams equal to range of a and b plus 2. Then we can go for edge color like black, alpha 0.8 density true, and label simulated. So these are the simulated uniform distribution. Also, I can go for theoretical. For example, x is equal to np dot a range of a and b plus 1. Then I will calculate PMF, rand in PMF, x, a, and b plus 1. This is the, we will compute theoretical PMF, and then we can plot it, for example, PLT dot, and these are the other information like PLT title, uniform distribution, x value, probability, legend, and all that we have. So there seems to be an error here because this one should not be here. And the problem is here, it should be b plus 1. So you can see here, this is the uniform distribution for a is equal to 1 lower bound and b is equal to 6 upper bound. This red one shows the theoretical PMF all 1 by 6, but for the simulation, because we randomly select, there is a little bit different. Next, I want to plot the CDF for the same example. So our a is equal to 1, b is equal to 6. We can calculate n as the number of outcomes. So n is simply b minus a plus 1. So we have a, b, and n. We can define x and CDF, right? So x is equal to np a range of a minus 1, b plus 2, right? In this way, we go a minus 1, a up to b plus 1, right? So if I want to print x here, you can see here. So this 7 here is just we want to show for plotting. Anyway, the number of outcome is 6, not 7. For the CDF 0, 1 by n, 2 by n, 3 by n, because cumulative, right? So np dot concatenate, and in here we go for 0, 1 by n, 2 by n, 3 by n. 0 will be the first one. Then np a range of 1 and n plus 1 divided by n. And the last one will be 1, okay? So NCDF equals to, this one should be here. Okay, so CDF, you can see here 0, 1 by 6, 1 by 6 plus 1 by 6, and so on, right? Now we can plot it. So PLT dot figure, and fig size is equal to 8 and 6. Then we will go for a step function, right? PLT, a step function, x, and where post, this is for, for incrementing. Then color, for example, is equal to blue, and label is equal to CDF of uniform random variable, where a is equal to a and b is equal to b. PLT step x CDF. All right, so here it is. This is a kind of a step function. Probability of less than 1 is 0. Less than 2, probability of less than 3, less than 4, less than 5, less than 6, and it goes to here. Next, we can go and plot for different range. For example, range is equal to 1 and 4, 1 and 6, and 1 and 3. So this is different combination for A and B. Then we go for plotting, plot figure, fig size is equal to 10 and 6. Then for A and b in range. So what we do here, we loop over the range that we have defined here, and then we generate some x values. So x is equal to np dot a range of a and b plus 1. Then we will calculate the PMF for each rate. So PMF is equal to rand int, because this is the uniform distribution, PMF, and in here we will pass x, a, and b plus 1. Then we will plot it, plt dot plot for each range, x, PMF, o dash, then label is equal to f, a is equal to a is equal to a, and b equals to b, right? Also, we can define the marker size here. Marker size is equal to 8. and we can add legend, X label, Y label, and create true. Okay, here we go. This is the probability for B starting from 1 to 4. So it is 1 by 4, 1 by 6, and 1 by 10. So one example is here. What is the probability of rolling a specific number like 4 on a fair 6-sided die, which follows a discrete uniform distribution over integers 1 to 6, right? So very easy. 1, 2, 3, 4, 5, 6. This is the possible outcomes. In here, A is equal to 1, B is equal to 6, right? Then n is equal to b minus a plus 1 is equal to 6 minus 1 plus 1 is equal to 6. And the probability mass function PMF for px is equal to 1 divided by n is equal to 1 by 6. And for x is equal to 4, then probability of 4 is equal to 1 by 6, which is approximately 0.1667. So we can do the same thing in Python. So in here, easy, a is equal to 1, b is equal to 6, n is equal to b minus a divided plus 1. And then x is equal to 4. Here are the parameters. Then PMF is equal to 1 by n, right? And we can go for example, PMF of 4. Print f probability of rolling x is equal to PMF of 4, right? So probability of getting 4 is 1 by 6. Next, what is the expected value, like mean, of a discrete uniform distribution representing the outcome of rolling a fair 8-sided die? 8-sided die. It means the outcome is 1, 2, 3, 4, 5, 6, 7, 8. Based on the equation that we have, expected value is equal to a plus b divided by 2. So a plus b divided by 2, right? 1 plus a divided by 2 is equal to 4.5. So we can write the same thing in Python. A is equal to 1, b is equal to 8, and mean is equal to a plus b divided by 2. And we can print it, which is 4.5. The next, calculate the variance of discrete uniform distribution for a random variable representing the number of a 4-sided die. So in here we have 1, 2, 3, and 4, right? Based on the equation, var x is equal to b minus a plus 1 in the square minus 1 divided by 12, right? So in our case, a is equal to 1, b is equal to 4. So in here, n is equal to b minus a plus 1, which is equal to 4 minus 1 plus 1 is equal to 4. Then 4 squared minus 1 divided by 12. So 15 divided by 12 is equal to 5 divided by 4, and which is 1.25. So calculation in Python, a is equal to 1, b is equal to 4 as the upper bound, then n is equal to b minus a plus 1, right? So in here, our variance is equal to n squared minus 1 divided by 12, and we can print the variance, which is 1.25. What is the probability that the outcome of rolling a 6-sided die is less than or equal to 3, right? So if we go for CDF, fx is equal to probability of x less than or equal to x is equal to floor of x minus a plus 1 divided by b minus a plus 1. So because this is a 6-sided die, so a is equal to 1 and b is equal to 6, right? And our x is equal to 3, based on the equation. N is equal to b minus a plus 1, which is equal to 6. And then f3 is equal to 3 minus 1 plus 1 divided by 6, which is equal to 0.5. This means that the probability of x less than or equal to 3 is 0.5. It means covering 1, 2, 3. So for coding in Python, we will go for a is equal to 1, b is equal to 6, x is equal to 3. This is the upper limit for CDF. Then CDF is equal to randint.cdf, and in here we will pass x, a, and b plus 1. B plus 1 because randint upper bound is exclusive. So then we can bring the CDF. It's 0.5. Okay, the last example, we want to simulate 5,000 instances of a customer being assigned to one of 10 customer service representatives that we label them from 1 to 10 at a call center, and each representative is equally likely to be assigned. We want to compare the sample mean and variance to their theoretical values, and also we want to plot a histogram of the simulated assignments overlaid with the theoretical PMF. We will go for random seed for reproducibility, so we say np.random.seed 42. Then A is equal to 1 first representative, and the last representative is 10. Number of our samples is equal to 5,000, and we calculate n is equal to b minus a plus 1, right? So this is our n. Then we will generate samples. So data is equal to randint dot random variables a b plus 1, and size is equal to n samples. Then we calculate the mean. So we will print np.mean of our data. This one 5.47. We can go for variance, print np.var of our data. So 8.28. And also we can go for the standard deviation, print np.std, right, of our data. So this is 2.87. So for the theoretical mean, we will go print a plus b divided by 2, which is 5.5. And for theoretical variance, print n square minus 1 divided by 12, which is 8.25. And for the theoretical standard deviation, simply we go for np.sqrt, np.variance of our data, which is 2.8. Right, next we go for plotting, plt.figure, the fig size is equal to 8 and 6. Then PLT histogram data in P range of A and B plus 2. In here, we should go for minus 0.5. And then density is equal to true color black alpha versus simulated. So in here, you can see we have added minus 0.5. We want to align the histogram bins properly for discrete data, like integers. We can also go for theoretical PMF. So PLT dot AXH line, horizontal line. Then here, for example, say 1 by n, color is equal to red, color is equal to red, and line style is dashed. Line style is dashed, label is theoretical PMF, plot title is okay. Then here, so we need to add the xtx here, plt.xtx, np a range of a and b plus 1, and okay. So let's see, data beans np dot a range. Okay, so here we go. This is the histogram of 5,000 customer assignment to 10 representative. Because it is random, there is some difference. But this red color is the PMF for uniform distribution. Okay, thank you very much for watching this video lecture. In this lecture, we learned about discrete uniform distribution. We studied definitions, properties, mathematical formulation, PMF, CDF, mean, variance, standard deviation. We also tried different examples and also coding in Python. Please practice and feel free to ask me if you have any questions by leaving a comment below this video. Thank you and see you in the next lecture.